This video provides an introduction to logarithmic functions. Recall that an exponential function is a one-to-one function, and therefore it has an inverse. The inverse functions of the exponential functions are called logarithmic functions. A logarithmic function with base b is a function of the form y equals log base b of x, where x is strictly greater than 0, b is strictly greater than 0, and b is not equal to 1, where the equations y equals log base b of x and x equals b to the y are equivalent. So let's just start with the first part of the definition. This is what a logarithmic function looks like. Y equals log base b of x. There's going to be some number where the b is, so we might have log base 3 of x. Now, what's inside the parentheses x must be positive. You can only take the log of a positive number. The base number, the b, must also be a positive number, and it cannot be equal to 1. The second half of the definition is extremely important. This is how we connect logarithmic and exponential functions. It's how we convert back and forth between the two, and this will be extremely important when we're solving exponential and logarithmic equations. So let's take a look at this. Y equals log base b of x. To rewrite this in exponential form, it looks like x equals b to the y. Anytime I'm learning something new in math, I try to link it to something that I already know. So to me, to convert from log form to exponential form reminds me of converting a mixed number to an improper fraction. Remember, if you had 3 and 5/6, to convert this to an improper fraction, we start on the bottom and it's 3 times 6 plus 5, and we go in this little circle to get 23/6. I see that same thing going from log form to exponential form. You're going to start with the b, which is on the bottom, and then I'm going to make this same circle. So b raised to the y is equal to x. Also remember that the logarithmic base and the exponential base always have to be the same number. So that can also help you with the rewrite. So we're going to practice converting back and forth between notation. So let's write each equation in exponential form. Log base 3 of 9 equals 2. Now, this is in the kind of flip-flopped from how it was written above. So my circle is going to go in the opposite direction. I remember that my exponential base and my logarithmic base have to be the same. So I'm starting with the 3. It's going to be 3 raised to the second power is equal to 9. And if everything is a number, we should get a true math fact, and 3 squared is indeed equal to 9. Let's convert log base 16 of 4 equals 1/2 to exponential form. The bases are the same, so we always start with the base. 16 raised to the 1/2 will be equal to 4. And again, we get a true math fact. We know that 16 raised to the 1/2 is the same as the square root of 16, and the square root of 16 is equal to 4. Now let's go the other direction. 81 is equal to 9 to the second power. Remember that the exponential base and the logarithmic base are always the same number. Our base in this example is 9 because that's what's being raised to a power. So we're going to have log base 9 of 81 is equal to 2. Personally, I'm more comfortable going from log form to exponential form, So I always double check it with my little circle method. So 9 raised to the second power is equal to 81. Let's convert 1/49 equals 7 to the negative second power to logarithmic form. We know that the bases are the same. Our base in this example is 7. Our argument, which is what we call inside the parentheses, is 1/49, and this will be equal to -2. We're going to use our ability to convert back and forth between logarithmic and exponential form to help us evaluate logs exactly. We want to evaluate log base 2 of 1/2. At this point, our knowledge of logs is very limited. However, our knowledge of exponents is pretty extensive. So we're going to convert this logarithmic expression into exponential form and then figure out the answer from there. So we have that log base 2 of 1/2 is equal to something. And we're trying to figure out what that something is. So we'll rewrite this in exponential form. We start with the base. We'll have 2 raised to the question mark is equal to 1/2. If you're more comfortable with an X than a question mark, please feel free to use an X. Now we need to figure out 2 raised to what power is equal to 1/2. And we just have to think about what we know about exponents. 2 raised to the negative first power is equal to 1/2. We know that that negative exponent takes our base to the opposite side of the fraction. So 2 to the negative first is equal to 1/2. Well, that means then that log base 2 of 1/2 is equal to -1. Let's try another one. Log base 100 of 10. Log base 100 of 10 is equal to something. And that something is what we're going to find out. We'll rewrite this in exponential form. 100 raised to what power is equal to 10? So let's think about it. What power can we raise 100 to so that we get 10? I only know that the square root of 100 is equal to 10, and the square root can be rewritten as the exponent of 1/2. So 100 to the 1/2 power is equal to 10. That means that log base 100 of 10 is equal to 1/2. It's equal to the exponent because that's what we were looking to find. That was our question mark. So there's 2 common bases that arise in logarithms. They're base 10 and base e. The logarithmic function of base 10 is called the common logarithmic function, and it's denoted f of x equals log of x. You'll notice that there's no base number. Since it is the common log, the one that is used most commonly, we don't write the log base. Kind of like with square roots, since it's the most common root, we don't write the index of 2. So with common log, they don't write the base of 10. Our other special one is a logarithmic function of base e. This is called the natural logarithmic function, and it's denoted f of x equals ln of x. So this ln of x is the same as log base e of x. And remember that e is 2.72. You have both an log button and an ln button on your calculator. These are the ones that are most common, so these are the 2 log functions that most calculators can do. Logarithmic functions and their graphs have some general properties. So recall our logarithmic function is f of x equals log base b of x, where x is strictly greater than 0, b is strictly greater than 0, and b is not equal to 1. The domain of the logarithmic function is not including 0 to positive infinity, just the positive numbers, and the range is all real numbers. Recall that the logarithmic function is the inverse function to the exponential function, and our exponential function had a domain of negative infinity to positive infinity, but a range of 0 to positive infinity. Also recall that inverse functions, the domain and the range switch. So we see that happen right here with our domain and range for exponential and logarithmic functions. Logarithmic functions have an x-intercept of 1, 0. It does not have a y-intercept and has a vertical asymptote on the y-axis. So again, this is just the reverse of our exponential function. The exponential function did not have an x-intercept, but had a y-intercept of 1, 0, and it had a horizontal asymptote on the x-axis. As inverse functions do, the x and the y just switched. When the base of a logarithmic function is greater than 1, the graph will rise from left to right. It'll look something like this. But when the base is in between 0 and 1, the graph will fall from left to right. Something like this. And lastly, logarithmic functions are one-to-one. Since f of x equals log base b of x is defined to be the inverse of f of x equals b to the x, when these two functions are graphed on the same plane, they will be symmetric about the line y equals x, like all inverse functions. Next, we'll be finding the domain of logarithmic functions. We just saw in our properties of logs that the domain is always not including 0 to positive infinity. That is, the argument of a log, it has to be strictly greater than 0. So to identify the domain of a logarithmic function, we're going to take its argument and set it strictly greater than 0. Now we have a polynomial inequality. There's two different approaches to solving a polynomial inequality. You can either graph the polynomial. We're looking for greater than 0, so we would be looking for portions of the graph that were above the x-axis, or the other option is to find the zeros of the polynomial and then make a sign chart to determine intervals that are positive or negative. I'm going to do the sign chart technique here, but this is an easy one to graph. You may be interested in the other technique. So this factors x plus 2, x minus 2. So that's going to give us zeros of a -2 and +2. So I'll draw my number line. Breaking up our number line at our two zeros. And now we want to choose a test point within each of these three intervals to plug in and determine whether our polynomial is going to be positive or negative in that interval. So let's choose something smaller than -2. We'll plug in -3, and I like to plug it into the factored form when it's more complicated, because then I can just look at the signs of the factors, but this would be an easy one to plug it into the original. So I'm going to plug into our original. -3 squared is 9, minus 4 is +5, so all numbers in this interval will be positive. Choosing a test point between -2 and 2, I'll choose 0. 0 squared is 0, minus 4 is going to be negative. And then lastly, choosing a number greater than 2, I'll choose 3. 3 squared is 9, minus 4 is 5. So all the numbers greater than 2 are going to give us a positive. We now want to choose the intervals where we are greater than 0, so that'll be the positive intervals. And now we just need to write that domain in interval notation. The domain will be negative infinity to negative 2, union 2 to negative infinity, or to positive infinity. Let's try another one. Let's find the domain for g of x equals log base 9 of x over x minus 5. We're going to start the same way. We know that the argument of a log has to be strictly greater than 0. And now we need to figure out where this rational is greater than 0. So I would definitely not use the graphing technique for this one because rationals are hard to graph. I'd much rather just find the zeros and do the sign charts. So we want to find zeros for the numerator and the denominator. So the 0 for our numerator is 0, and then the 0 for our denominator is 5. So we'll break up our number line at 0 and 5 and choose some test points to plug in. Something less than 0, so I'll choose negative 4. Plugging negative 4 in, I'm going to get negative 4 on top and negative 9 on bottom. Negative divided by a negative is going to leave us a positive. Choosing a number between 0 and 5, I'm going to choose 1. Plugging 1 in, I'm going to get 1 over negative 4, so that'll be negative. And then lastly, choosing a number greater than 5, let's choose 10. Plugging 10 in, I'll have 10 over 5. Well, that's going to be a positive. Since our argument has to be greater than 0, that means that we're looking for the positive intervals. Our domain in interval notation is negative infinity to 0, union 5 to infinity.